I'm a research engineer, and my specialization is on industrialized and robotic construction, and how can we use all these data-driven approaches for this industrialized and robotic construction. So I told that it will be short, but I guess I took more than like 4-5 minutes to explain this. But like this is like ஒரு குறும்படம் மாதிரி கடந்த 10 வருஷமா நான் என்ன பண்ணிட்டு இருந்தேங்கிறதோட ஒரு 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 ஜிஸ்ட் மாதிரி இது. So based on this, I'll quickly go into the actual meat of the presentation. So AEC field, we don't encounter this word very often, right? Like architecture-ங்கிற வார்த்தை encounter பண்ணுவோம், engineering-ங்கிறது construction தனித்தனி silos-ஆ பார்த்துப்போமே தவிர, like it's not kind of like looked at together as a single entity. Maybe Chennai Trade Fairல பார்த்தீங்கன்னா AEC Trade Fairனு போடுவாங்க, but apart from that, like the industry is really fragmented. So that's what is the motivation behind this entire presentation. So typically when we start a design, right, like whenever we do a building design, whether it be academically in college or like even for clients in reality, you start with a design brief and then you do a conceptual design. அதுக்கப்புறம் அதை கொஞ்சம் மெருகேத்தி we'll do preliminary design. And then we also kind of like add all the technical stuff, make it much more detailed, and we go into the detailed design phase. And then we go into construction management phase. Once we decide, okay, fine, like this design is fixed, let's go and construct it on site. Then we engage all the construction managers, purchase of the materials, procure all the materials, and then construct it on site. And then finally, it's being constructed. And after construction, we operate the building. When I say operation, if I am building, we are operating the building, or like we are literally living inside the building. So there is an aspect of facility management, the facility being the building, and then we are managing the facility throughout its life cycle. So from the design brief all the way until operations, there are multiple professions which are being involved. So typically architecture is a domain. We are heavily involved from design brief to preliminary design stage. And then we need the support of like design engineers, or like, let's say structural engineers or energy consultants, or like, let's say estimators and contractors in order to detail out the design based on like whatever is available in the market. And then we need like construction managers and project managers support in order to execute the construction. So typically this is what is like the spectrum of AEC activities, right? Like architecture, engineering, and construction. So where exactly data-driven design comes into play here? So typically when we design a building, right, like whether it be the architecture block at SRM University that you're sitting in at Ramapuram, or whenever we design, we make a lot of iterations. So in the geometry, so whenever we make these changes, right, like staircase inge vekalama, illati vandu like roofing material eppadi vekalama, or the should we orient the building in a different way. Whenever we make such geometrical manipulations, there is something in the performance of the building which is changing. So left side like you see a GIF which is representing the changes in design. Right side like you're representing like a graph. I don't want to go into the technical details of the graph, but like just imagine that each of these bars, right? One is energy performance, one is structural performance of the building, one is daylighting performance of the building, and then cost of the building construction, and then like the time it takes to construct the building. So as you change your design, you experience that like these parameters also vary accordingly. So how do we kind of like get a balance across these parameters despite the changes in the building? And typically or a residential scale building, like these are simplistic parameters, but when you go to like, let's say right now you might have seen in the news that like there are buildings which are 3D printed using robots, there are buildings which are constructed using robotic technology, or even like much more complex commercial buildings or office buildings. So those buildings, when you are thinking about them, you also need to think about these additional parameters, like these in the red bar, so that is like manufacturing time or like the robotic throughput. What I mean by that is like typically if you go and meet a client, they'll be like, in the budget building, I want the building to be this much energy efficient or LEED certified and so forth and so on. But the moment you incorporate robotic construction into it, you also need to think about like how long will it take for the robot to construct the building, or like will the robot be able to construct the building and things like that. So how do you measure that performance factor is also a matter of concern. So in the varying performance factors, how do you design a building holistically? So as I told, as the scale and complexity of the building increases, like let's say that like you're designing a factory, or you're designing an industry, or like a skyscraper or something which has so many different systems, For a building, it's not like a simple product, right? You have walls, you have foundations, ceilings, roof slab, coffer slab, and things like that. And even you have MEP conduits and things like that. So in the system, the complexity also kind of like increases. So typically in a building, you'll encounter the facade, the envelope, and then like the fall ceiling or like different systems, MEP systems and like structural systems and so forth and so on. So each of these, right, like how much ever we might like to say that like an architect is responsible for all of this in large scale projects. For example, when you Chennai metro rail construction, for example, like Hilton Hotel, when the airport and the buildings, there will be a lot of different stakeholders who are involved. It's not just the architects, it's going to be architects, engineers, structural engineers, daylighting performance analyst, and energy analyst, and so forth and so on. So the system responsible. If we ask them to design the best building possible to meet their expectations, each of them might come up with like one option. For example, here are 4 options. One structural performance engineer might say that like the option that you see on the top left corner, that's the most structurally robust design option. Whereas like the energy analyst might say that like in the right side option is the most convenient to route MEP, mechanical, electrical, plumbing services, and so forth and so on and so on. Or like the energy engineer might come and say that like in the or building now is the most energy efficient, the rightmost corner one at the bottom. Or the architect might say that like if you orient the building and then the building has to have this massing in order to support daylighting friendly design, that's an option. But like ஒரு single project ஒரு building தானே கட்ட முடியும், 4 கட்ட முடியாது இல்லையா? So how do you kind of like make that holistic decision where you have all these parameters satisfied, but like there is one particular design? So typically how the process is right now is that like we start with the conceptual phase, right? We start with a massing diagram or like a massing model, and then we make some changes, like we decide on the number of floors and like the height of the building, the orientation of the building, and so forth and so on. And then preliminary phase, we might evaluate the building for like, let's say, structural performance. So the structural engineer might say that like, okay, I'll come up with like 4 different options, and then I'll evaluate for the best possible option. So the objective, when I use the word objective, what I mean is design goal. So structural engineer, the most efficient option, the one which has highest structural performance. So on the key graph, A1 and A4 have like more structural performance indicated by green, right? So on the render design, we'll go to the next phase. And let's assume that like an architect kind of like does lighting analysis, and then they are like lighting jastiya irukra building design, envelope design, or like the windows, how you position them and things like that. So their criteria is that like to maximize the lighting factor. That is what is indicated by the upward arrow next to the word lighting factor. So in the null option, like in the end option, adhiga lighting factor identify, they will kind of like push those 2 options to the next phase. Let's assume that like the next phase you're evaluating the building for building cost. So budget on the meet pannu. So like you'll have to meet let's say ஒரு 50 லட்ச ரூபாய்க்குள்ள இந்த பில்டிங்கை கட்டி முடிக்கணும் அப்படின்னு சொன்னாங்கன்னா you will have to minimize the cost. It shouldn't exceed that 50 lakhs. So whichever of the 4 design options and the material inputs, the BOQ, bill of materials எல்லாம் சொல்லுவாங்க இல்லையா, அது எல்லாத்தையும் கால்குலேட் பண்ணா எது ரொம்ப கம்மியான பட்ஜெட்ல வருதோ அதை செலக்ட் பண்ணுவோம். And then we push it on to the next phase. And then energy analyst energy consumption kammiya irukanum, LEED certification padi appdin sonnanga, then we generate a couple of different options, and then let's assume that like 2 options are selected with the most minimal energy consumption. So இது ஒரு சீக்வென்ஸா போயிட்டு இருக்கு இல்லையா, ஒன்னுக்கு அப்புறம் இன்னொன்னு அப்படிங்கிற மாதிரி. So and then finally comes the construction management stage, and this is where like architects and project managers kind of like have like a tiff. So what happens is that like typically they value engineer the project. ஸோ நம்ம ரொம்ப ஃபேன்சியா இந்த டிசைன் கட்டினா சூப்பரா இருக்கும் அப்படின்னு நினைச்சிட்டு எல்லாத்தையும் டிசைன் டிராயிங்ஸ்லாம் ஃபைனலைஸ் பண்ணி கொடுப்போம். பட் கன்ஸ்ட்ரக்ஷன் மேனேஜர் லொஜிஸ்டிக்ஸ் ப்ராப்ளம்னால மெட்டீரியல் டெலிவர் ஆகல, இல்லாட்டி இந்த காஸ்ட் ஃபுல்ல பண்ண முடியாது, லேபர் காஸ்ட் ஏறிடுச்சு, கோவிட்ல ஷட் டவுன் வந்துருச்சு, இந்த மாதிரி 1008 ரீசன்னால தே வேல்யூ என்ஜினியர் த டிசைன். ஸோ தே மைட் பி லைக் எந்த டிசைன் கன்ஸ்ட்ரக்ஷன் ஸ்கெட்யூலுக்கு இணக்கமா இருக்குன்னு பார்த்துட்டு தே வில் செலக்ட் த மோஸ்ட் efficient construction time design. For example, in the null option, these 2 options are the most efficient for construction management. Let's say சீக்கிரமா கட்டி முடிக்க முடியுங்கிற ஆப்ஷன் அந்த green colorல இருக்கு இல்லையா, so they will select that. But the problem with such a sequential approach is that if you notice that like energy consumption க்கு எது best option choose பண்ணாங்களோ அதை அப்படியே பின்னாடி பக்கமா ட்ரேஸ் பண்ணி பார்த்தீங்கன்னா இட்ஸ் கமிங் ஃப்ரம் லைக் அ லீஸ்ட் பர்ஃபார்மிங் ஸ்ட்ரக்சரல் அண்ட் லைட்டிங் ஃபேக்டர் டிசைன். ஸோ பெஸ்டா இருந்த ஸ்ட்ரக்சரல் டிசைன்ல இருந்தோ இல்ல பெஸ்டா இருந்த லைட்டிங் ஃபேக்டர் டிசைன்ல இருந்தோ இது ரெண்டும் வரல. இன்ஸ்டெட் இட் இஸ் கமிங் ஃப்ரம் அ சப் ஆப்டிமல். ஸோ அந்த வேர்ஸ்ட்ங்கிறது பதிலாக யூஸ் அ வேர்ட் சப் ஆப்டிமல், டெக்னிக்கலா அது சப் ஆப்டிமல்னு சொல்லுவாங்க. ஸோ சப் ஆப்டிமல் டிசைன்ல இருந்து செலக்ட் பண்ணுவோம். ஸோ வி ஆர் இதை வந்து இன்னும் சிம்பிளா உங்களுக்கு புரிய வைக்கணும்னா the problem is that ஒரு விஷயத்தை சரி பண்ண பார்த்தோம்னா அந்த பாய் எப்படி பின்னாடி வந்துட்டே இருக்கோ அதே மாதிரி வந்து இன்னொரு விஷயம் அப்படியே வந்து இதுவாயிட்டே இருக்கும். ஒன்ன கூட்ட பார்த்தோம்னா நான் குறையும், இல்லாட்டி இன்னொன்னு குறைக்க பார்த்தோம்னா ஒன்னு கூடும். ஸோ ஃபார் எக்ஸாம்பிள் கன்ஸ்ட்ரக்ஷன் டைமை குறைக்க பார்த்தோம்னா எனர்ஜி எஃபிஷியன்சி குறையலாம், இல்லாட்டி வந்து ஸ்ட்ரக்சரல் பெர்ஃபார்மன்ஸ் குறையலாம், இல்ல ஸ்ட்ரக்சரல் பெர்ஃபார்மன்ஸை கூட்ட பார்த்தோம்னா எனர்ஜி பெர்ஃபார்மன்ஸ் குறையலாம். பட் வி டோன்ட் வாண்ட் டு கைண்ட் ஆஃப் லைக் மேக் ட்ரேட் ஆஃப்ஸ், ரைட்? ஒன்னுக்காண்டி இன்னொன்று விட்டு கொடுக்க வேணாம் இல்லையா? ஸோ வாட் ஐ டிட் in my PhD essentially was that எல்லா அப்ஜெக்டிவையும் ஒரே நேரத்துல எப்படி சாட்டிஸ்ஃபை பண்ண முடியும். ஒரு பில்டிங் ஸ்ட்ரக்சரலாகவும் ஸ்டேபிளா இருக்கணும், எனர்ஜி ஃப்ரெண்ட்லியாகவும் இருக்கணும், அட் தி சேம் டைம் காஸ்ட் எஃபெக்டிவாகவும் இருக்கணும். ஸோ அந்த மாதிரி எல்லா இதையும் ஸோ ஐ யூஸ் திஸ் மீம் ஜஸ்ட் டு எக்ஸ்பிளைன். ஸோ டோன்ட் கெட் மீ இன் அ ராங் சென்ஸ். ஈஸியா புரியுறதுக்காக வந்து ஒரு இதுவாகவும் இருக்குமே அப்படின்னு சொன்னேன். ஹோப் த ஐடியா இஸ் கன்வேட் ஹியர். ஸோ இதை எப்படி பண்றது அப்படிங்கும்போது, ஸோ during my PhD, like what I did was like, is this problem specific to AEC industry, architecture, engineering, construction industry? No, it's existing in other industries as well. For example, I guess like there are people who are interested in bikes here. நீங்க காலேஜ்க்கு டெய்லி வரதுக்கு வந்து பைக்ல கம்யூட் பண்ணுவீங்கன்னு நினைக்கிறேன். ஸோ each one of us have a preference for bike, right? Few people want a bike which looks good. Few people want a bike which is reliable. Few people want a bike which is within their budget. So இந்த மாதிரி டிஃப்ரெண்ட் ஆப்ஷன்ஸ் இருக்கு. திஸ் இஸ் த கன்சியூமர் வியூ பாயிண்ட். இப்போ நான் ஒரு பைக் வாங்குறேன்னா எனக்கு பிடிச்ச மாதிரி நான் இதுல இருந்து ஏதாவது ஆப்ஷனை செலக்ட் பண்ணுவேன். But from a designer viewpoint, let's say Bajaj or KTM or Yamaha, இவங்கெல்லாம் வந்து அந்த மேனுஃபேக்சர் பண்ணும்போது the factors that they take into account are, so இந்த இவ்வளவு விஷயத்தையும் அவங்க பார்க்கணும். So the bike has to have ample amount of mileage, it has to be cost efficient. So இதுல வந்து 1,95,000 ரேட் போட்டிருக்கு. So 1,95,000. So that's not affordable for everyone. So for example, if I would have been that, நான் காலேஜ் ஸ்டூடெண்டா இருக்கும்போது I wouldn't be able to afford that. My parents wouldn't be able to afford that much value for a particular bike. So I might look something which is on a much more budget friendly market, right? At the same time, if I'm shrinking the budget of producing a bike, I shouldn't also kind of like lose out on the performance metric. ஒரு பைக் வந்து 50,000 ரூபாய் வருதுங்கிறதுக்காக அது மைலேஜே தரலன்னா then it makes no sense, right? We won't be able to buy that bike. இல்லாட்டி வந்து it gets easily damaged during, it doesn't have structural performance now, then the cost reduction makes no sense. Because so we don't buy bikes or cars or whatever the product may be, even the cell phones or the laptops that we have, we look at holistic performance. Same thing applies for building, and then the same problem is existent in other engineering fields as well. So what do they do and how can we learn from them? That is what my PhD was. So they use this technique of data-driven design, and this is where I want to introduce what exactly data-driven design is. So இப்போ வரைக்கும் நான் சொன்னது எல்லாமே வந்து we do a sequential process, right? So the best way to handle this might be generate lot of different combinations and then make a selection. Simple ஒரு எக்ஸாம்பிள் சொல்லணும்னா, if we want to make the most satisfying selection, பாண்டி பசாருக்கு போய் 10 கடை ஏறி இறங்கி நம்ம ட்ரெஸ் வாங்கணும்னா we'll make பட்ஜெட் ஃப்ரெண்ட்லியாவும் எடுப்போம், இல்லாட்டி வந்து பிடிச்ச மாதிரியும் எடுப்போம், இல்லாட்டி வந்து லக்ஸூரியஸா எடுக்கணும்னாலும் எடுப்போம். பட் லைக் இட் gives you that satisfaction if you explore all the options possible. So same way these engineering fields develop catalogs of design options. So for example, bike-la this wherever you see, if you can see my cursor, there is a suspension unit here. So this is a suspension unit, and then to design that suspension unit they use data-driven design. And what they essentially do is generate this catalog full of different types of like bike chassis or suspension design, and then evaluate them for different performance factors. So towards your left side of your screen, you see these filters, right? So in the ஒரு filter on this a performance parameter like strength, stiffness, mass, cost, drag, heat flux, manufacture time, factor of safety, and all these things. So இது எல்லாத்துலயுமே வந்து for example manufacturing time வந்து கம்மியா இருக்கணும், so it should be minimized. Strength should be maximized because it needs to be stable enough to bear any impact from accidents and like day-to-day routine wear and tear and things like that. So all of these different design options are generated. And then in the kutti graph mari theriyudhu, that is nothing but each point in there represents one design element in the catalog that you see on the right side. So in the ஒரு point, how it performs on multiple factors and evaluate panni, they make the best possible solution, or select the best possible design which is fitting all these different parameters together. Okay. And this data-driven technique has been used in the design of cycles or design of other engineering products. It has even been used in the design of drones. So இப்போ நீங்க நிறைய பேர் drone shows பார்த்திருப்பீங்க, or else even in like colleges you might have seen it in culturals where drones are used. So each drone by itself is not useful for anything, right? அதுல ஒரு camera fix பண்ணுவாங்க, இல்லாட்டி ஏதோ ஒரு payload fix பண்ணுவாங்க. So it needs to carry that weight of the payload. So at the same time, ஒரு drone easier பறக்கணும்னா it has to be lightweight. Anything that ஒரு ஹெவியான பால் தூக்கி போடுறதுக்கும் ஒரு லைட்டான பால் தூக்கி போடுறதுக்கும் டிஃபரன்ஸ் இருக்கு இல்லையா? So drone has to be lightweight to fly easier. At the same time, it has to be stable enough to carry heavy payloads. Like let's say நீங்க ஒரு DSLR கேமராவை மவுண்ட் பண்ணி அனுப்புறீங்கன்னா it needs to be able to withstand that weight. So how can you achieve both of these contrasting features? They use data-driven design to lightweight so that they achieve the perfect geometry which can give best of both worlds in Ramari. It is lightweight as well as it is stable enough to carry ample amount of load in Ramari. So can the same principle be applied for building design? That was a key question that I tried to address through my PhD. And what I did was I developed a machine learning based data-driven design framework. I would call it framework. That's a tool, it's a framework. And then just giving a brief gist of what the framework is. It can generate multiple building design models automatically. And when I say automatically, it doesn't mean that or architect they won't be modeling it or something of that sort. The architect will be able to kind of like guide the system to model in a particular way. So the designer aspect or the instinct is still there. And then you analyze all these different generated designs for different parameters. Like let's say structural performance, daylighting performance, and build cost. This is a sample of the performance parameter. Project to project, it might differ. For example, when you have a project, they might not be interested in daylighting performance. They might be interested in cost and structural performance alone. So, under the parameter, analyze. So, depending on the project, you can set what parameters you need. And then once it's analyzed, once you make the selections, then the system will be able to select the most or the best possible building solution for the given design problem. And it's not like, okay, there is some computer software where I give all these things and then it does some magic and then it spits a design at me. You need to step by step. நம்ம யூஸ்வலா பண்ற மாடலிங் அண்ட் அனாலிசிஸ் டூல் ஆர் லைக் அந்த டிசைன் பண்ற ப்ராசஸ்க்கு இது ஒரு உறுதுணையா இருக்கிற ஒரு டூல் மாதிரி. இட்ஸ் an assistive tool rather than a replacement tool. So just a sample of how these things work, ஒரு குட்டி வீடியோ சாம்பிள் மாதிரி. So this was a code that I developed where you can kind of like, or a script rather, where it will kind of like generate multiple design options based on like different input parameters. You can change the way that the building is oriented, or the height of the building, or the shape of the building, the angle, and like all the different systems which go into there. And then once all these different design elements are created, then idellame vandu will be stored in a catalog. And then on the catalog I have like an interface where like you can select, okay, here I'm comparing these designs for 3 parameters. One is machining time, which is basically a robot, the construct panona, how long will it take? Material cost, basically how much cost will go into constructing this. And then compressive strength, which is basically a structural engineering parameter. So compressive strength on the maximum machining time or robotic deposition time should be minimum. Construction cost should also be minimum. So so you make all these different filter changes. So in the filters you will see that the graph kind of changes. So each point represents one design item. So it's saying that like for the given filters, this is the best possible option. And then that point corresponds to one. Okay. And another thing is that I developed this and then model panambodu and one important thing is that like a lot of these different systems go into the building, right? Like let's say envelope systems, MEP conduits, and like நீங்க உட்காந்துருக்க பில்டிங் சுத்தி பாத்தீங்கன்னா sometimes if it has a fall ceiling அதை உடச்சு மேல பாத்தீங்கன்னா it will have different services inside it. டக்ட் இருக்கும், அதுக்கப்புறமா டக்ட் ஹேங் பண்ற இடம் இருக்கும். இது எல்லாமே நிறைய விஷயங்கள் இருக்கும், சர்வீசஸ் அண்ட் சிஸ்டம்ஸ் அண்ட் பிளம்பிங் சிஸ்டம்ஸ் இந்த மாதிரிலாம். ஸோ அது எல்லாத்தையுமே வந்து எப்படி ஆட்டோமேட்டிக்கா ஜெனரேட் பண்றதுங்கிறதுக்கு ஒரு ஸ்கிரிப்ட் ஒன்று டெவலப் பண்ண, தட் வாஸ் ஆல்சோ பார்ட் ஆஃப் மை PhD. So it will kind of like create placeholder elements for you. So you just feed in an empty massing of a building, and then it will populate all the different kind of floor slabs, columns, beams, fall ceilings, and like all the different systems which go into the building, the envelope assembly. So நம்ம ஊர்ல பாத்தீங்கன்னா walls are typically made of concrete, right? Like it's flush concrete, it's homogeneous concrete. அதை உடச்சு பார்த்தா உள்ள ஒன்று கான்கிரீட் இருக்கும், இல்லை செங்கல் இருக்கும், இது ரெண்டு தான் இருக்கும், அதுக்கு மேல பிளாஸ்டர் இருக்கும். But if you go to like let's say Kashmir or like கொஞ்சம் குளிர் பிரதேசம்லாம் போனீங்கன்னா there will be multiple layers inside the wall, and that is for a reason. உள்ள நம்ம உட்காந்தா குளிரக்கூடாதுங்கிறதுக்காக இன்சுலேட் பண்றதுக்காண்டி there will be multiple layers. So the way that you construct the construction details, everything kind of like changes. So அதுக்கு வந்து this technique will be helpful, where it automatically generates all these different components for you given an empty massing. And finally these data, so இந்த நிறைய நம்பர்லாம் நீங்க பாக்குறது வந்து இட்ஸ் நத்திங் பட் லைக் வால் திக்னஸ், ஃப்ளோர் ஸ்லாப் திக்னஸ், டக்டோட சைசிங், அதுக்கப்புறமா வந்து விண்டோ எத்தனை பேன்ஸ் ஆர் லைக் வாட் இஸ் த ஷேப் ஆஃப் த விண்டோ அண்ட் ஆல் தோஸ் திங்ஸ், அதோட கோஆர்டினேட்ஸ் அண்ட் திங்ஸ் லைக் தட். And then you can interactively change the length of the building, breadth of the building, floor height, இந்த மாதிரி இதெல்லாம் சேஞ்ச் பண்ணிட்டு then you can select whichever is the best option. So previous example மெஷினிங் டைம், கம்ப்ரஸர் ஸ்ட்ரென்த் எல்லாம் கம்பேர் பண்ணோம். இங்க வந்து எனர்ஜி கன்சம்ஷன், ஹீட்டிங் லோட், டேலைட்டிங் ஃபேக்டர், பில்ட் காஸ்ட் இதெல்லாம் கம்பேர் பண்ணிட்டு இருக்கோம். ஸோ கம்பேர் பண்ணி எது பெஸ்ட் ஆப்ஷன் அப்படின்னு we can choose it. So this was the framework, the data-driven framework which came out of my PhD. So it can be accessed from multiple devices per se. So this is what came out of my PhD. And so now that I've given a brief background about data-driven design, I want to step in or segue into robotic construction. So we know that like there is robotics in multiple fields which are taking a lead right now. So how does robots find a place in construction? So just giving an example with the project. So here I will talk more about the NASA competition that I was part of, where I used the same framework that I developed, but for designing a building specific to the rules of this competition. So NASA around 2018 or 17, I guess, they hosted a competition called the 3D Printed Mars Habitat Challenge. So it was a multi-year, multi-phase competition. So 2017 end or 2018 ஆரம்பிச்சு it went until 2020. So there were multiple levels, and each level there were teams which were shortlisted and like they progressed to the next level. So initially there were around 80 teams, out of which Penn State was also a team. And we ended up being the finalists of the competition through multiple phases, and then we won the second place. So அந்த ஒரு பெரிய டீம்ல ஒரு இத்தனோண்டு பார்ட் ப்ளே பண்ணேன் நான். So I wasn't like, I wouldn't claim credit for the entire success of this. I was just playing a very, very meager minor role. So just explaining about the design brief for this competition, there were two levels. So one was a virtual construction level, where we envisioned that if this building is going to be constructed in Mars, how will we do that? And then another thing was the actual construction level, where we demonstrate the same robotic construction technology down here on Earth. Because இப்போ மார்ஸ்க்கு போயிட்டு வர முடியாது, போயிட்டு வரதுக்கு வண்டி இல்லை, ராக்கெட் வந்து இன்னும் இது பண்ணல. So we have to kind of like demonstrate things down here on Earth because of the remote nature of it. So we had to, whatever we design, we had to kind of like demonstrate the technology. So giving some background, Norman Foster's office and then FL Wright's office also competed in this competition. So initially they were kind of like shortlisted for 1 or 2 or 3 phases. If you might have seen in the internet, there was a proposal by Norman Foster's company or FL Wright's company. I don't know whose it was, but like they had like a concept where you could 3D print with ice in Mars and things like that. So those were like really good concepts. But when it came to actual demonstration down here on Earth, they weren't able to do that because those were like far-fetched, like science fiction movies la vara mari solluvom illaya. So those were a little bit not practical. I wouldn't say that it's not practical at all, but like down the lane in 50 years or 100 years, maybe it is possible with the technologies that we have. But right now with the technologies at our disposal, those ideas were not feasible. So eventually, or fortunately, we were able to kind of like progress through multiple phases because we tried to keep the system very practical. So for virtual construction level, we were designing for majorly a thin atmosphere, cold temperatures, and low gravity. So Earth Mari, it's not the same in Mars. It has a very thin atmosphere, which means like UV rays and like cosmic radiation can enter the atmosphere, and that's why we can't like walk bare-bodied in Mars. Skin cancer vandrum. So அதனால வந்து அந்த ஷீல்டிங் இது பண்றதுக்கு you will have to stay in a very enclosed environment, and your building should protect you from such radiations. So if you're just going to construct with concrete, very இங்கே மாதிரி 9-inch wall construct பண்ணோம்னா that will still allow penetration of radiation. So you need, fun fact here is that Marsல எந்த material யூஸ் பண்ணாலும் irrespective whether it be concrete or some other innovative material, your walls has to be a minimum of 2 feet thick. 2 அடி இருக்கணும். ஒரு சின்ன எக்ஸாம்பிள் சொல்லலாம்னா நியூக்ளியர் ரியாக்டர் பார்த்துருப்பீங்க, கூடங்குளம்லயோ இல்லாட்டி வந்து நம்ம கல்பாக்கம்லயோ, இதுல எல்லாம் பாத்தீங்கன்னா அந்த ரியாக்டரை சுத்தி வந்து ஒரு மீட்டருக்கு செவர் கட்டி வச்சிருப்பாங்க. ஸோ தட் லைக் none of the radiation escapes that. So அந்த 1 meter concrete will prevent the radiation from escaping. Same thing applies for Mars. You need at least 2 feet of wall thickness in order to prevent radiation from entering the building. And 2 feet of wall thickness வச்சு நம்ம வந்து பில்டிங் டிசைன் பண்ணியிருக்கோமா பண்ணலாம், but will it look good? It might or might not. Will it serve other parameters? For example, energy efficiency ல அது பண்ணுமானா it will have impact. So that is where like the data driven aspect comes in. How can you manipulate all these different parameters together? So, and especially this robotic construction is kind of like tricky. You know, what happens is that we used an industrial robotic arm for concrete 3D printing. So when I say robotic construction, I want to be specific. Here I'm talking about additive construction, or what we colloquially call 3D printing of concrete. So as you might see in this video, everything might seem as if it's going good. Like we might design and then the robot might construct it, but suddenly it might fail. No one expected that, right? So the kutti sample, it failed. It's just a waste of a little bit of material. But imagine if we have like a huge wall which is drastically higher than our normal or average human height, or like it's bigger than us. And if it fails, அது வந்து ஆக்சிடென்ட்ஸ் லீட் பண்ணலாம். யார் மேலேயாச்சும் விழுந்துச்சுன்னா அவங்களுக்கு மண்டை உடையலாம், இல்லாட்டி அடிபடலாம், இல்லாட்டி வந்து நிறைய வந்து பட்ஜெட்ரி கன்ஸ்ட்ரெயின்ஸ் வரும், கன்ஸ்ட்ரக்ஷன் லாஸ், cost laws and things like that. So we need to ensure that nothing fails in robotic construction. So typically in construction, we don't worry about this right up early in the design phase. எல்லா டிசைனும் பண்ணிட்டு தென் வி கிவ் இட் டு லைக் கொத்தனாரா இருக்கட்டும், இல்ல சித்தாலா இருக்கட்டும், இல்ல கார்பெண்டரா இருக்கட்டும், இல்லாட்டி வந்து லைக் இட் கேன் பி ஸ்கில் லேபர் லைக் ஃபால் சீலிங் இன்ஸ்டலேஷன் கைஸ் ஆர் MEP இன்ஸ்டலேஷன் கைஸ். They'll take care of it. They're trained to do that. But robotic construction, it's still nascent, right? So sometimes it might fail. So how do we ensure that it doesn't fail? We need to think about these construction constraints up during the design phase. So அந்த geometry இப்படி இருந்தா விழுகலாம், இப்படி இருந்தா விழுகாம போகலாம். So you need to think about all these things during the design phase itself, which is new to the construction industry. For example, architects, we don't think about construction up early. We might think in a very vague term, but we don't think in terms of detail. But we need to do that. So how do other industries tackle such problems? For example, car manufacturing, they use a lot of robots. Automobile engineering, they use a lot of robots. So they use something called digital twins. So they basically simulate the robotic construction process even before anything is manufactured. So can this level of sophistication be applied to the construction sector? Yes, it can be. And that is what we did in the NASA competition. But again, it's not as easy as simulating a car manufacturing plant, because like ஒரு car 50 லட்சம் pieces manufacture பண்ணுவாங்க, ஒரு phone அதே மாதிரி கோடிக்கணக்கில் மேனுஃபேக்சர் பண்ணுவாங்க. பட் பில்டிங்ஸ் தே டிஃபர் ஃப்ரம் சைட் டு சைட், ரைட்? லைக் ஃபார் எக்ஸாம்பிள், if there are 40 people in your class, one person might design a building in a different way, another person might design the building in a drastically different way. So how do you kind of like come up with like a robotic construction system which is universal to all these things? So that is challenging. And especially what the challenge is that in 3D printing, what we do is we model. Basically, we generate a 3D model. We slice the model, basically virtually divide it into like horizontal layers, and then we translate it into something called a machine code. It is nothing but like the robot on the end direction traverse பண்ணனும்ங்கிறதுக்கு ஒரு route map மாதிரி. Let's assume that it's a Google map for the robot, okay? So point A to point B போறதுக்கு Google map எப்படி வந்து route காமிக்குது, அதே மாதிரி ஒரு robotக்கு இந்த geometry ஃபுல்லா print பண்ணனும்னா what route it has to take. That is what they call as a toolpath. So we translate the model, sliced model, into a toolpath, and then it's simulated using whatever equipment we are 3D printing it with. So you guys might have encountered small scale 3D printers, tabletop 3D printers, which print plastic and metal and all those things. But the problem with concrete is that like நம்ம ஒரு குட்டி விஷயம் print பண்ண போறது இல்லையா, ஒரு full building print பண்ணும்போது there are areas where it might fail. For example, concrete, when it has tapered surfaces, it will be prone to failure, because you might have seen that there are these, if you go to a typical construction site, they have form work for concrete and then they pour concrete. ஒரு 7 நாளைக்கு வந்து அதை cure பண்ண விட்டுட்டு they remove the form work once it's solidified. So until that, like the concrete is going to be in a viscous state. So same thing, 3D printingல உடனே வந்து concrete வந்து டக்குன்னு காயாது, டக்குன்னு cure ஆகாது. So slanted areas might fail, which means you are limited to constructing straight walls. Or if your building is hollow, which in most cases it is difficult to construct it using 3D printing. So how do you tackle all these issues? So in reality, let me give an example. Let's assume that we are 3D printing a slab, a rectangular slab. Chinnada or example. We slice it into two different toolpaths. So when I said route map, right, like Google Map Mari, so it can, in the same rectangular slab can be constructed, or a beam can be constructed using both of these toolpaths. Toolpath A, which is like concentric, toolpath B, which is like zigzag and different layers. One layer இப்படி இருக்கும், ஒரு layer வந்து இந்த axisல வந்து இதுவாயிட்டே இருக்கும். And we have to, இப்போ நான் பார்க்கறது எல்லாமே visual, my human brain can understand this, but in order to feed this to a computer, I need to convert it into a code, which is basically what I call toolpath code. இது ஒன்றும் இல்லை, ஆட்டோமேட்டிக்காக வந்து இந்த ஜாமெட்ரியை வந்து ஒரு கோடாக மாற்றி கொடுக்கும். And then you feed it in the robot, and then that is the command for the robot. And the robot will perform the same action accordingly. So right now we printed both of these slabs, right? Rectangular slabs. But there are minor nuances that we should notice. One is toolpath B was good in structural performance when we actually measured compressive strength. மேல வந்து compression test பண்ணாங்க, lateral flexure strength பண்ணாங்க, இதெல்லாம் பண்ணும்போது structural performance was good enough because of like the cross bracing னு சொல்லுவாங்க இல்லையா, அந்த zigzag lines ஓட adhesive nature-னால, பிடிப்புனால. But again, because of the same zigzag nature, it had complex robotic maneuvers, which meant that like there were vibrations at turns. I would like to give a quick example here. Imagine that you're driving a bike or a car. வேகமா போயிட்டு டக்குன்னு ஒரு டர்ன் எடுத்தீங்கன்னா வந்து யூ எக்ஸ்பீரியன்ஸ் தட் சென்ட்ரிபியூகல் ஃபோர்ஸ், ரைட்? லைக் டக்குன்னு இந்த சைடு போவீங்க. இந்த ஃப்ரெண்ட்ஸ் படத்துல வடிவேல் வந்து கேட்ல பிரேக் போட்டுட்டு விழுவார் இல்லையா, அது மாதிரி. ஸோ சேம் திங் ஹேப்பன்ஸ் டு தி ரோபாட். ஸோ திஸ் ரோபாட் வில் எக்ஸ்பீரியன்ஸ் வைப்ரேஷன்ஸ் அட் த ஷார்ட் டர்ன்ஸ் பிகாஸ் அது வேகமா இது பண்றதுனால. அண்ட் பிகாஸ் ஆஃப் தட், concrete will deform because concrete is like a paste. So imagine like you're holding a toothpaste tube in your hand, and then வேகமா அதை அமுக்கிட்டே இது பண்ணீங்கன்னா வந்து டூத்பேஸ்ட் இங்கேயும் அங்கேயும் தெரிக்கும். So same thing happens to concrete because it's a viscous material, which means it's going to result in less shape accuracy. So ஒரு performance factor better-ஆ இருந்தாலும் இன்னொரு performance factor வந்து குறையுது. So how can you kind of like optimize for this? So that's where we deployed data-driven design. And same goes, whenever you have like a building which has like these tapered walls, you will experience such failures of concrete. So ஒரு wall multiple layers of concrete இருக்கும். And the innermost layer, whenever there is like a tapered portion like this in the 3D model here, it might experience bead failures. So how, and that is because ஒரு லேயரும் வந்து ஸ்டாகர் ஆகி இருக்கிறதுனால சென்டர் ஆஃப் கிராவிட்டி வந்து தள்ளிட்டே போகும். ஸோ இட் வில் பி கைண்ட் ஆஃப் லைக் டு ஃபார்ம். இமேஜின் டு பி லைக் ஒரு 10 புக்கை அடுக்கி வச்சு பாருங்க, அப்படியே பக்கத்துல ஒரு குறிப்பிட்ட ஆங்கிள் வரைக்கும் தான் அது தாங்கும், அதுக்கப்புறம் எல்லாமே விழுந்துடும். ஸோ சேம் கான்செப்ட் அப்ளைஸ் ஹியர் இன் த மோஸ்ட் சிம்பிளிஸ்டிக் ஆஃப் டர்ம்ஸ். But how can you kind of like solve this? So the design variables that we can control in order to solve this is angle of taper. So ரொம்ப ஸ்லாண்டா இல்லாம ஒரு அளவுக்கு ஸ்லாண்டோட டிசைன் பண்ண முடியும் பில்டிங். பட் would we want to be constrained with that? எப்பவுமே வந்து ஸ்லாண்டே இல்லாம டிசைன் பண்ண முடியுமா? It will be very monotonous, right? Like us as architects, we want design freedom. We want the building to look good. We want the building to kind of like have good aesthetic features and like for other reasons as well. So on the parameter control pannalam, or we can change the material consistency. Magically, if we invent a concrete mix which sets instantaneously, then all the problem is solved. But unfortunately, we don't have such a concrete mix yet here. So what else can be done? So another problem is that, like as you can see in this 3D printed sample here, in the corner wherever I'm hovering my cursor, you can see that there are lots of wiggly lines, right? So whenever the robot had to make such acute angles, same example that I told a couple of moments before, when you drive a car or a bike and then make a sharp turn, you tend to kind of like swerve. So same thing happens here. The concrete kind of like deforms because of the vibrations of the robot. But such type of deformations are not so good, right? Like you don't want such unforeseen changes in the geometry. So how can you change that? So challenges is over extrusion at edges and corners which are sharp, and the design variables that you can, when I say design variables, nothing but like இந்த வாலோட திக்னஸை மாத்தினா இது வந்து ரெமெடி பண்ண முடியுமா, இல்லாட்டி இந்த மெட்டீரியல் மாத்தினா. ஸோ தோஸ் வேரியபிள்ஸ் வாட் கேன் யூ சேஞ்ச்? So we can either change the fillet radius at the edges of corners, or you can change the speed of the robot at the corners. Similar to like ஒரு டர்ன் வரும்போது வந்து ரெடியூஸ்ட் ஸ்பீட்ல வண்டி ஓட்டுற மாதிரின்னு வச்சுக்கோங்களேன். ஸோ யூ கேன் ரெடியூஸ் த ஸ்பீட் ஆஃப் த robot, but like it doesn't work at all times either. Another problem is that these are some pictures from the finals itself. So we eventually reached the finals of the competition. So 80 teams or 80 plus teams, and 4 teams were selected for the final. So Penn State was one among that. And we, when we actually 3D printed a full scale building, what we designed, we faced a lot of problems in the finals as well. So for example, concrete beads here, you can see that it failed on the innermost surface where it had that angle of taper. And then sharp edges as such in the building, those had like deformations, and it had similar issues. So if in the ஒரு bead fail ஆகுறது வந்து ஒரு இடத்துல problem இல்லை, அது வந்து ஒரு domino effect மாதிரி. So if you have to print on top of that, if there is no support structure beneath it, then it will cantilever and the bead above also will fail. A concrete filament above that layer also will fail, which means the entire structure can collapse. There is a possibility for that. So it's a very crucial element to be taken care of. So how did we kind of like manage all these things? So it's very challenging because you need to consider multiple systems. What and all do you need to consider? You need to design the building itself, which means it's not just the concrete walls. You have like energy systems, you have furnitures, you have other things which go into the building, window positions, wall positions, and all those things. That is the systems design. You need to design the tool path. So as I told, it can either be concentric or on a simple rectangular slab, concentric, illati zigzag and rende format. But when it comes to a whole building, which is like a much more complex geometry, there are multiple ways that you can design these tool paths. And you also need to design the material. So if you look into concrete mixtures, there are admixtures, binders, aggregates. எல்லாம் அந்த ரெசிபின்னு சொல்லுவாங்கல்ல, சப்பாத்தி மாவுல கசைகிற மாதிரி தண்ணி, உப்பு, சப்பாத்தி மாவுங்கிற மாதிரி கான்கிரீட்டுக்கு அட்மிக்ஸ்டர், பைண்டர், ஆக்ரிகேட் நிறைய இருக்கும் இல்லையா. ஸோ அது எந்த காம்பினேஷன்ல வந்து மிக்ஸ் பண்ணா இட் வில் ஹாவ் தட் கியூரிங் ப்ராப்பர்ட்டிஸ், அதையும் நம்ம டிசைன் பண்ணணும். Will it be amenable to the design that we have in hand? That also has to be taken care of. And we also need to take care of the production design. Basically, all of this that I told, a robot is not like a start button. Okay, என்கிட்ட ஒரு மெஷின் இருக்கு, அதை நான் ஸ்டார்ட் பட்டன் அமுக்கினேன்னா அது வந்து எல்லாத்தையும் பண்ணிடும், அப்படி கிடையாது. robot is nothing but like ஒரு ஹேண்ட் மாதிரி இமேஜின் பண்ணிக்கலாம். என் கையில ஏதாவது ஒரு டியூப் இருந்தால் தான் நான் அதை டெபாசிட் பண்ண முடியும். ஸோ சேம் வே robot is connected to a tube, and then the tube is connected to a material feeding system. And then that material feeding system is next to the same geometry that you're going to 3D print. So it needs to be designed in a way that like the construction site is like hassle free. Nothing kind of like hits each other on the money. So production setup design. So all these things have to be designed simultaneously, which typically doesn't happen in the construction industry. Ipodaki, when we design typical residential or commercial buildings, which are normally constructed using traditional design, we don't think about all these things at one go. We do think about these at separate instances, but in robotic construction, all of this need to be clubbed and it needs to be thought about from the starting of the design phase. So how do we do that? So கொஞ்ச நேரத்துக்கு முன்னாடி நான் ஒரு டேட்டா ட்ரிவன் ஃப்ரேம்வொர்க் என் பிஹெச்டில கிரியேட் பண்ணணும்னு காமிச்சாங்க. ஸோ ஐ யூஸ் த சேம் ஃப்ரேம்வொர்க் ஹியர். ஸோ ஐ வாஸ் ரெஸ்பான்சிபிள் ஃபார் திஸ் பார்ட் ஆஃப் த காம்படிஷன் ஃபார் Penn State, the NASA competition. So I use the framework to model, generate a lot of different models, analyze them for different performance factors like structural performance, daylighting, build cost, energy, and then robotic construction time, and then select whichever was the best on all these performance factors. So this was my meager teeny tiny role that I played in the NASA competition. And then going into the details of it, so we modeled the building. So I developed a script which can kind of like take care of like the entire modeling. So instead of showing the actual script, I'll tell what and all were the components. So we had the floor slab with the trenches for all the different services. We had like walls, partition walls for, so because it was an extraterrestrial building, or at least envisioned to be constructed in extraterrestrial environments, we went with a modular approach. So ஒரு மாடியூல்ல வந்து ஏதாவது ப்ரெஷர் ப்ராப்ளம் இல்ல ஃபயர் ஹசார்ட் நடந்தா கூட you can shut it off and then save the rest of the modules. And even in future, if you want to construct additional modules, if you construct it as modules, it will be easier. And we went in with a modular approach. So that is why you see these different circles. So finally, we ended up with like a 4-module version, which had all these different amenities like bedrooms, living quarters, dining space, working space, and then like we had like a upper floor which had like a floor slab and a working space, a gym space around there, and then like we had like separators between each of these modules which are electronically controlled. We had the mechanical, electrical, plumbing systems. As I told, நம்ம சென்னையிலேயோ இல்லாட்டி வந்து சதர்ன் இந்தியாலேயோ கான்டினென்டல் டெம்பரேச்சர்ல we don't நம்ம ஃபேன் யூஸ் பண்ணுவோம், லைட் யூஸ் பண்ணுவோம் to meet our day-to-day ends. But like when in extreme climates you need specific equipment. For example, நம்ம ஸ்பிளிட் ஏசியோ இல்லாட்டி வந்து ஒரு ஏர் கண்டிஷனரோ ஒரு ரூமுக்கு போடுறதுக்கு பதிலாக ஒரு என்டையர் பில்டிங் பண்ணோம்னா இட்ஸ் வெரி காம்ப்ளெக்ஸ் ப்ராசஸ். ஸோ அந்த ஏசி யூனிட்ல இருந்து பைப் எப்படி வருது, அது வந்து ஃபிளஷ்டா இருக்கா, வால்குள்ள போயிட்டு வெளில வருதா, இல்லாட்டி வந்து தரக்கடியில வருதா, அண்டர் ஃப்ளோர் சிஸ்டமா, ஓவர் ஹெட் சிஸ்டமா, இது எல்லாமே யோசிக்கணும். அண்ட் தட் இம்பாக்ட்ஸ் யுவர் ஓவரால் பில்டிங் ஜாமெட்ரி as well to design it in a holistic or aesthetic way. We had like a hydroponic food production system, and then finally comes the enclosure or the enclosure, the concrete enclosure. So again, like we use the framework that I developed in order to generate all these different catalog of design options. So it'll automatically generate multiple different design options for you with varying parameters, different slope angles, different configurations of these like the modules. So here in this slide, what you see is like a catalog of design options. Mela vandu or sample kandi or 8 design option kaamichirukken, but we actually in reality generated around 713 or so design options. And then we compared those design options for different performance factors. For example, number of floors based panni, whether it's 4 modules or 3 modules or like 1 floor or 2 floors. And then in the graph la zoom in panningena, it's nothing but each of these points are like one particular design. Concentration factor, which is basically a structural performance parameter, like stable இருக்கணும்ங்கிறதுக்கு ஒரு parameterன்னு வச்சுக்கோங்க. And then robotic deposition time. So stress concentration factor ஜாஸ்தியா இருக்கணும், which means right side நோக்கி போகணும். Concentration factor கம்மியா இருக்கணும், ஏன்னா pain points கம்மியா இருக்கு, இதுதான் அதை மீன் பண்ணும். So it should be towards the left side. Robotic deposition time should also be towards the left side. So essentially ஒரு ideal design is somewhere here in the plot. This might be a little bit confusing, but like the data-driven aspect took care of it. And essentially, we have to analyze, right? On the graph on generate, we have to have analysis and analysis results. So we perform structural analysis on all these, performed toolpath failure detection, basically, and then the areas of concrete are prone to fail. So on the image above, you can see the red areas are prone to fail, green areas are good to stand. So we have to manipulate the geometry so that the red areas are removed and treated in some other way. We also did some toolpath clash analysis, which is basically இதுதான் நான் சொன்னேன், நிறைய எக்யூப்மெண்ட் தேவைப்படும். ஸோ இட்ஸ் நாட் ஜஸ்ட் ரோபாட் விச் இஸ் லைக் ஒரு பட்டன் போட்டால் அது வாட்டுக்கு வேலையை பார்க்க அப்படி கிடையாது. சுத்தி முத்தி நிறைய ஆக்சசோரியல் எக்யூப்மெண்ட் இருக்கணும், அதோட ஃபீடர் சிஸ்டம். ஸோ வி ஹேட் லைக் விச் ஐ வில் டைவ் இன் டு டீப் couple of slides later, இன்னும் கொஞ்சம் டீப்பா நான் எக்ஸ்பிளைன் பண்றேன். So we had a robot for 3D printing, we had a robot for picking and placing objects. So we had to simulate the entire process for clashes, whether ஒன்னுக்கு ஒன்று இடிச்சுக்குமா அது கன்ஸ்ட்ரக்ட் பண்ணும்போது, இதெல்லாம் வந்து சிமுலேட் பண்ண வேண்டியது இருந்தது. And as I told, this again is a plot explaining how we were able to narrow down the design from like, let's say இங்க டோட்டல்னு போட்டு 713 or number போட்டுக்கலையா. So that was the total number of design options that we generated. So we compared it for multiple factors like total usable area ஜாஸ்தியா இருக்கணும், deposition time, robotic deposition time கம்மியா இருக்கணும், stress concentration factor கம்மியா இருக்கணும். ஸோ இது எல்லாத்தையும் எப்படி இது பண்ணணும். ஸோ 713 ஆப்ஷன்ஸ்ல இருந்து கடைசியா 5 ஆப்ஷனுக்கு கொண்டாந்து நிப்பாட்டணும் through the detailed design stage, and that was possible through the data-driven framework that we developed. And finally, these two were the design options which were selected. So for the virtual construction level, we ended up with a 4-module version. For the actual construction level where we demonstrated this, we ended up with a 2-module version. And we did some simulations. If it were to happen on Mars, on the robotic system, how will it construct it? So we right from excavation to like 3D printing completely, all the walls and everything, and how it places all the other elements like the trenches, the duct surfaces, the windows, and all those things. And this was if it were to happen on Mars. So down here on Earth during the finals of the competition, we had to demonstrate it live, right? So adukku we developed another simulation which exactly created a digital twin of our production setup. So we had a truckload of equipments which was delivered. We had like a huge tank for water to mix the concrete, or a syntax tank mari imagine panikonga. We had a silo, this triangular thing that you see, that's like a huge silo which consists of the concrete powdered concrete. So ஒரு பெரிய கண்டெய்னர்னு வச்சுக்கோங்க. And then we had like a pump which will mix the water and the concrete mix, which is what you see here. And then we had two robots, one robot which can 3D print. So as you can see, in the hose connector in the robot, so the robot will kind of like guide the hose and according to the shape of the geometry. And we had another robot which was responsible for picking and placing objects like windows, other ducts and services and things like that. So we even simulated who will be responsible for what, like labor, as in laborers in the sense, us teammates were the laborers here. So yaar endinda idukku monitor pandradhukku responsible avana and the level to be simulated. And once we did this 4D simulation, so this is the actual simulation, and then this is the actual setup towards the right side. So as you can see, left and right compare panni paakumbodhu, it's almost like 95 to 100, 98% similar. Not 100%, I wouldn't call it 100% because we had minor variations on site because of site constraints, but almost like more than 95% அதே மாதிரி simulate பண்ணது என்னமோ அதையே வந்து நாங்க வந்து செட்டப் பண்ண முடிஞ்சது. And these are few snippets from the competition where we have this huge industrial robotic arm 3D printing our entire building, the 2-module version. And for sense of scale, you can see that like there are human beings around this. So it was like almost a 4-meter tall structure. So it was not a teeny tiny structure. And these are few pictures from the NASA competition finals, which we eventually won the second place in. So to our knowledge, I would like to put a small disclaimer here. I might be wrong, but to our knowledge, even in IIT Madras, you might have seen 3D printing of buildings, but there is a very minute nuance here. Most of the buildings that are 3D printed in either Dubai or like let's say IIT Madras or like in any other place in the world, even USA or like Europe, everything is like straight wall. So what they do is like if they want to print a cuboidal room, they print it in different kit of parts, allow it to cure, and then assemble it together. Roof வந்து தனியா print பண்ணி they lift it using a crane and then place it on top of that. So ours was the world's first fully enclosed tapered concrete structure, 3D printed without any support structures. So we didn't have any internal support structures to support the taper. So to our knowledge, I might be wrong again here, it was the world's first fully enclosed tapered concrete structure. So that is how it is different from other 3D printed concrete structures, so that it allows that taper and different geometries. And again, for a sense of scale, NASA being a very huge organization, they had to do all these different tests for structural performance. So typical compression test வந்து நீங்க ஒரு civil engineering student போய் பேசுனீங்கன்னா ஒரு குட்டி ஒரு experimental setup மாதிரி இருக்கும். அதுல வச்சு வந்து they press with different sorts of hydraulic weights. அந்த செட்டப் வந்து கிட்டத்தட்ட ஒரு 5 அடி உயரம் ஒரு 4 அடி அகலம் தான் இருக்கும். But because it was an entire building, instead of that particular setup, they had like a excavator to do the compression strength test. So a fun fact here is that Caterpillar நம்ம கிண்டில கூட இருக்கு, இந்த கத்திப்பாரா ஜங்ஷன் இந்த கம்பெனியோட ஒரு ஆஃபீஸ் இருக்கு நம்ம சென்னையில. So they manufacture these different JCBs, excavator, not JCB, that's a different company, but like excavator. So this number here, 319, so this 3 depicts excavator and 90 depicts 90 tons of weight. So that was the weight that was put on top of the structure to test the stability of this. So eventually the structure crumbled. This was unreinforced concrete structure. It didn't have any reinforcements inside. So for an unreinforced concrete structure, what happened was, for example, நீங்க வந்து ஒரு pull-up barல வந்து கையை வச்சு இது பண்ணீங்கன்னா your body tends to go up, right? So same thing happened as the excavator kind of like pushed the structure with the bowl. அதோட அந்த wheels வந்து started raising up, which means it had the structure provided ample amount of like counter force. So as you can see, it lifted up a little bit. So it was able to withstand this weight for approximately 45 seconds, which was like impressive for like unreinforced concrete structure. So that was like a key takeaway point. But like again, it did crumble after like 45 seconds, but it was good for the structural test. So now that I've explained about data-driven design and robotics in construction, what do I do right now? இப்போ நான் என்ன பண்ணிட்டு இருக்கேன், இதெல்லாம் பண்ணேன், ஓகே ஏதோ வந்து கொஞ்சம் கொஞ்சம் பண்ணேன். What do I do? So I work at this federal government entity called National Renewable Energy Laboratory here in the US. I hold a joint appointment with NASA and enroll together. So I work there as a research engineer. So இதுக்கு முன்னாடி நீங்க பார்த்த இந்த பில்டிங்லாம் வந்து it's just raw concrete structures, right? So it's homogeneous material. But typically in a building there are multiple such systems. So நீங்க இப்போ வந்து ஒரு ஏர்போர்ட் பில்டிங்ல போயிட்டு வந்து Mailer, you'll have all these different systems, and these are there for a reason. Without these systems, you can't have the right microclimatic ambience, which means வேர்த்தூத்தும் இல்லாட்டி நமக்கு ஒரு கம்ஃபர்டபுளா இருக்காது. அந்த ஒரு உள்ள ஒரு தெர்மல் கம்ஃபர்ட்டோ இல்ல ஒரு working comfort irukadu, which means the building will be unusable. So all these different systems are necessary for a building to function. So as you can see in this picture, there are different laborers who install all these things, right? So my current research role is to explore how robotics can be used to install all these different systems in addition to, let's say, concrete wall construction or other construction. So holistic or building a full robots which construct on what is needed and what are all the technologies that are needed. That is what I work on right now in my current role. And with that, I end my presentation. I guess I went a little bit overboard the given time. Sorry about that. And just to end it on a fun notion, there might have been 3 types of audiences after this presentation. ஒரு சில பேர் ஆஹா அப்படியா அப்படின்னு கேட்டிருக்கலாம், ஒரு சில பேர் சொன்னதெல்லாம் கேட்டுட்டு அண்ணனுக்கு ஒரு தப்புங்கிற மாதிரி இருந்திருக்கலாம், ஒரு சில பேர் இதெல்லாம் ஒரு பிரசன்டேஷன் ஆன்ற மாதிரி இருந்திருக்கலாம். Hopefully, like I didn't have much of audience 2 or audience type 3. If I did have, sorry about that. Sorry for the boring presentation, and hope I did not bore you folks on a Wednesday morning. And thank you so much again.
Thank you, sir. I would like to take questions from the audience. Kindly post them in the chat box. First question is, apart from construction, what are the different fields that robotics can be used with regards to architecture?
So apart from construction, as in like construction is what like we build. I'm a little bit confused by the question, but like architecture, once you design everything, then like you will have to construct in order to see it in reality, right? So that is where like tangibly robotics can be used. And if I am to understand this question in a different way, what are all the avenues for robotics in architecture and construction? As I told, 3D printing is one avenue, and then like using robots to pick and place objects is another, and autonomous. Sorry about that. Like, are you guys able to hear me?
Yes, we are able to hear you.
So as I was telling, the variety of things that can be done is like 3D printing in construction can be robotic, picking and placing objects in construction can be robotic. At the same time, the next level of robotics would be like, let's say in 20 years or 25 years, autonomous robotics will take place. A lot of you might have heard of these Tesla cars, or like, let's say, autonomous vehicles, right? Vehicles that can make their own decisions. So imagine like an excavator which can automatically go to the site. You give it a GIS based site plan and it can excavate all the foundation holes by itself. That is a possibility for robotics in construction. To design a building, to place walls autonomously in construction, that is also a possibility. So there are multiple ways that it's a very nascent area. It's still kind of like growing. So there are multiple avenues.
Some of the creative limitations in designing a 3D building, given how 3D printing is being widely used in architecture.
Yeah, I would like to point back to like the same slide that I showed before. So few of the creative limitations right now is that like most of the 3D printing companies and the startups that you see around you guys in India or in Dubai or in any foreign country, including the US here, is that most of them are straight walls. So as I told, or roof print pannona, they don't print it like all the way with a single robot. They print it on the floor separately, allow it to cure, pick it up and place it. And then like organic shapes are not very possible. As in you might have seen like wiggly walls which are 3D printed, but if you notice it very keenly, they don't have this taper, or they can't have anything which is cantilevered as of now. Reinforcing 3D printed structures is also very manual right now. It's not robotic. So typically what they do is they print cavity walls, leave a gap in between, put reinforcement bars in between and fill to kind of like hold it together. So that is the way that reinforcement is done in like 3D printing, which again has some geometrical constraints. So you can't print very organic or like designer friendly shapes using 3D printing as of now in construction, but it's slowly getting there. And regarding is 3D printing being widely used in architecture right now, global percentage or number 100% 3D printing market, I might call it 5%. So it's still very, very meager, but it's slowly kind of like increasing the market share. So once we solve these questions of how to print multi-story buildings or tapered walls in a much more universal fashion, then this 5% will increase to, it has the prospects to increase to, let's say, 25% or 30% of the construction industry.
So the next question is for technological
Yes, absolutely. Technological advances will directly impact methods of construction and architecture, and it's high time that like architecture community adapts to these technological advances and then upgrades to these technological advances so that we don't lose out on the field. So for example, like technology வளர வளர அதை எப்படி நம்ம கன்ஸ்ட்ரக்ஷன் ஃபீல்டுக்குள்ள இன்கார்பரேட் பண்றோம்னு நம்ம வந்து அப்டேட் ஆகிட்டே இருந்தோம் ஆர்கிடெக்சர் கம்யூனிட்டினா, then we'll be able to kind of like have more say in the design. Rather, if we give that decision making to someone else, let's say that like a robotic technologist will take care of it, I don't have to worry about it, or a civil engineer might take care of it, I don't have to worry about it, then what we'll end up having is that like they will make the key design decisions. நம்ம ரொம்ப ஃபேன்சியா ஒரு டிசைன் கொண்டு போய் கொடுக்கலாம், but like because the construction technique and the technology won't support this, they will value engineer and then construct it according to whatever is possible based on their knowledge. So that is why it's essential that like architects kind of like spend considerable or significant amount of time in adopting these new technologies in construction.
So the last question is, what are the constraints when it comes to data-driven design in architecture?
So one constraint with data-driven design is that there is a viewpoint that data-driven design will make architecture very regressionistic. For example, ours is a very creative field, right? Either data-driven design சொல்லும்போது any டக்குன்னு கேட்கும்போது வந்து many people might think that like, okay, this is like some random software, some random machine which is taking all the decisions, whereas an architect am I playing a role, but it is not that case. It does have some limitations in terms of overall objectify பண்ற மாதிரி இருக்கும். We as designers, we think instinctively, and the hand-mind coordination சொல்லுவாங்க, while we sketch, we design intuitively. So in the data-driven design, everything comes up with like a model. So that hand-mind coordination in terms of a sketch, that gets slightly lost because we are dealing with like a model and mind coordination here, which is a little bit harder to kind of like take. But again, on the sketch is what will inform the data-driven approach here. So the key constraint is that transition from like sketch to design to a model to design approach. So how are we going to think in terms of three-dimensional performance factors and like ஒரு டிசைனை வந்து வெறும்னே வந்து ஒரு ஏஸ்தட்டிக் ஒரு விஷுவல் அப்பீல் மட்டுமே பார்க்காம ஆர் லைக் ஹியூரிஸ்டிக்ஸ்ன்னு சொல்லுவாங்க. ஃபார் எக்ஸாம்பிள் ரூல் ஆஃப் தம்ஸ்ன்னு சொல்லுவோம் இல்லையா, இங்க வந்து கதவு பக்கத்துல உடனே வந்து ஸ்டார் கேஸ் வைக்கக்கூடாதுங்கிறது ஒரு ஹியூரிஸ்டிக் டெசிஷன், தட் இஸ் அ வெரி இம்ப்ளிசிட் டெசிஷன் தட் வி கேன் டேக். அண்ட் தென் லைக் இப்போ வாசப்படி பக்கத்துலேயே வந்து ஒரு ரொம்ப ஸ்லோப் சர்ஃபேஸ் வைக்கக்கூடாது டிசேபிள்டு இருக்கும்போது, அப்படி இதெல்லாம் இன்ட்யூட்டிவ் டெசிஷன்ஸ் தட் வி கேன் டேக் வென் யூ ஆர் ஹேண்ட்லிங் அ ஸ்மால் ஸ்கேல் ப்ராஜெக்ட். But just imagine like a large scale project, like you might encounter many such heuristic points, and அது எல்லாத்துக்குமே நம்ம வந்து டைம் ஸ்பெண்ட் பண்ணி டிசைன் பண்ண முடியுமாங்கிறது is going to be tricky. So how can we kind of like automate certain processes which are mundane? That is where data driven design comes in. So those are the constraints. How do we kind of like objectify what is needed and then still have that subjective experience of design? So that is like the constraint in data driven design.
Session and a great learning experience for us. I now request the head of the department, SRM SEAD Ramapuram, Architect Naveen sir, to give the.
And before I wrap up, just 1 second, so I just wanted to give an acknowledgement. So this is the number of people who worked in the NASA team. So it wouldn't do justice if I don't kind of like share their expertise here. So ஒரு பெரிய டீம்ல தான் நானு. So all credits to the entire team, and I just wanted to acknowledge them here as well.
வணக்கம் நவீன்.
Hi sir.
நவீன், உங்க பிரசன்டேஷன் ரொம்ப அருமையா இருந்தது. நீங்க சொன்னீங்க ஸ்டார்டிங்லயே தூங்கிடுவேன் அப்படின்ட்டு. யாருமே தூங்கல, எல்லா ஸ்லைடுமே ரொம்ப ரொம்ப இன்ட்ரெஸ்டிங்கா இருந்தது. ஓகேவா? அண்ட் ஒன் மோர் திங், நீங்க வடிவேலையோ டூல் ஆக்கிட்டீங்க. அவர் பாஷையிலே சொல்ல போனா உங்க பிபிடி பார்த்து நாங்க எல்லாருமே ஷாக் ஆயிட்டோம். அதுதான் உண்மை. உங்களுக்கு பேஸ் மட்டும் ஸ்ட்ராங்கு, பில்டிங் ஸ்ட்ராங்கு. தென் கட்டிடக்கலையை அடுத்த பரிமாணத்துக்கு எடுத்துட்டு போற உங்க முயற்சிக்கு எங்களது வாழ்த்துக்கள். ரொம்ப அருமையான பிரசன்டேஷன். தேங்க்யூ சோ மச் நவீன்.
Thank you so much, Ramesh sir, and I would like to especially thank Vijayashree ma'am again here, because she was the bridge for this to happen. So thanks ma'am again for, and I was one of the students of Vijayashree ma'am back during undergrad. So ஒரு சின்ன விஷயம் என்னன்னா, like I was trained as an architect, same as how you guys here are in the attendees வந்து எல்லாருமே architects தானே. So I was also trained as an architect, and that was the profession which gave me this big picture thinking. வேற ஃபீல்ட்ல இருந்து நம்ம கத்துக்கிட்டு இது பண்ண முடியும்னு. ஸோ இட்ஸ் அ வெரி பியூட்டிஃபுல் ப்ரொஃபஷன். அண்ட் தென் அதுல வந்து மென் பண்றது, நான் சொல்ற ரொம்ப கிரிஞ்சா இருக்கலாம், ஒரு பழைய ஃபேக்கல்ட்டியை ரொம்ப புகழ்ந்து பேசுறாரு, பட் இட் வாஸ் த ட்ரூத். She gave utmost design freedom when I was in undergrad, and that kind of like nurtured my thought process. So credits to her as well. நான் இப்போ இங்க இருக்கேன்னா அதுக்கு ஒரு விதத்துல மாமன் காரணம். ஸோ தேங்க்யூ ஸோ மச் மேம்.
நாட் ஓன்லி நவீன், உங்களுக்கு மட்டும் இல்லை, எங்களுக்கு ஜஸ்ட் மிகப்பெரிய ஒரு பெஞ்ச் மார்க்.
Thank you, Naveen. Thank you. Thanks a lot, Naveen, for accepting in your busy schedule.
See you ma'am. Anytime for you guys. Thank you.
All the best for all your future endeavors. Best wishes from our end.
Thank you so much, ma'am. And any kind of like questions, or if you want help in your
hope to see you in another session when you come to Chennai. We'll invite you to SRM SEAD. Sure.
Thank you, ma'am.
Thank you, Naveen.
Thank you everybody for your participation. We have another webinar coming up at Metaverse by architect Roxy Krishna. Look forward to your participation.
And thanks Padma as well for hosting. See you all.
I would like to end this video event off with a note from our sponsors. Any cultural event would not be possible without our sponsors. Hashtag 2022 is presented by our title sponsor, By Guy Sanitation, co-sponsor, Forest Life, events builders, also sponsors, Purvika, Z Salon, and Lead. We would like to thank all our sponsors for making hashtag 2022 possible. Thank you.
Forest Ply, a line among plywoods. Forest Ply range of products: Platinum, Gold, BWR, MR, Flush Door, Block Board, Shuttering. Forest Ply, a line among plywoods. Forest Ply